Now that you've looked at the run-of-the-mill octet rule-obeying Lewis structures, I want to look at a few exceptions that nevertheless obey the octet rule, but don't obey the simple rules that we've seen before. Basically, looking at that table again, that boron, carbon, nitrogen, oxygen, and fluorine, in terms of the numbers of bonds, boron makes 3, carbon 4, nitrogen 3, oxygen 2, and fluorine 1, and the number of non-bonding pairs. Boron and carbon don't have non-bonding pairs typically. Nitrogen has 1, oxygen 2 sets, and fluorine 3. Notice boron doesn't really make up the octet. Boron molecules generally have only 6 electrons in the outer valence shell. These others, the carbon, nitrogen, oxygen, fluorine, on the other hand, generally have 8. This table, remember, only works for atoms when the atom is neutral. And in a sense, we've incorporated the basic idea of counting charge when we've come up with that. Remember, an atom looks around at its valence shell and asks, how many electrons, n, do I feel that contribute to my charge? And the number that is determined is by taking 1/2 the bonding electrons plus all of the non-bonding electrons. And that's an important point here. We don't have to figure n for atoms that obey the octet rule. So for example, if I have a molecule like nitrogen trichloride, I don't have to count out the charge that nitrogen feels. Nitrogen should have 3 bonds, 1, 2, 3, because there are, after all, 3 chlorine atoms, and then I have to remember to put that non-bonding pair. Chlorine, by the way, is just like fluorine. It should make 1 bond and have 3 sets of non-bonding pairs. We'll look later at a situation in which 3rd and 4th and 5th period elements can sometimes exceed the octet rule. Right now we're only looking at octet-obeying molecules. But there are some interesting situations that arise that require a little bit more imagination, and we want to look at those. It also gives us a chance to look a little bit at the notion of valence. For example, consider the nitrate ion. Not nitrogen trioxide, but the nitrate ion. If I analyze this molecule in terms of how I'm going to set up a bonding pattern, firstly I see that nitrogen is a single copy atom. It comes first in the formula, so I'm almost certain that nitrogen goes in the middle. Therefore, I've got 3 atoms of O to hang on the nitrogen, and I'm just going to hang them like this. I also see I have 1 negative charge, and I'm supposed to have remembered that if I have a negative charged oxygen, inevitably it means that I have 1 bond and 3 sets of non-bonders to that negatively charged oxygen. I'm now in a situation where I might say, well, I want 1 more non-bonding pair for nitrogen, but notice I've got 2 oxygens with a real problem here. So I might analyze this in this way. I can make 4 bonds to a nitrogen atom. I can go ahead and put my 4th bond there. Then I can put 2 sets of non-bonders to oxygen, and I'm following the usual set of rules for oxygen. On the other hand, now I have a positive charge on this nitrogen. Remember, up here I have a negative charge on that oxygen that had the 1 bond and 3 sets of non-bonders. This nitrogen now has a positive charge, so far what I have is a neutral structure, positive canceling negative. Throw 3 more non-bonders on this O here, that gives that a negative charge, and I have an overall ion here with a negative 1 charge. I've got formal charges on 2 of my oxygen atoms, and then a formal positive charge on my nitrogen atom. So that's a relatively simple way to do this. Reviewing the rule of the figuring n here, this nitrogen atom in the middle says I see 2, 4, 6, 8 electrons, half of which are really mine. That's 4, and nitrogen is a 5A element. So it's supposed to be feeling 5. So it's feeling 4, it should feel 5, it's +1, it's deficient. The oxygen, on the other hand, sees 2, 4, 6 completely belonging to itself. Half of that bonding pair there makes 7. So an oxygen, of course, is a 6A element. It's supposed to be feeling 6, and this oxygen here and this oxygen here are actually, both those are feeling 7, so that's why they're both negatively charged. Now I can also ask the question, why did this oxygen down here be the one that I gave the neutral charge to and put the double bond with? There's nothing that says I couldn't, for example, rewrite my structure this way, in which I now put my negative charge on these 2 oxygens, and make the right-hand oxygen double bonded and therefore neutral. Or, for example, I could rearrange this in one more way and have the top oxygen double bonded and the other two oxygens negatively charged. These are what we refer to as resonance structures. All three of these, and actually all three of these structures represent an approximation, if you could imagine adding these in your mind, to the real structure. Sometimes we use double-headed arrows to signify the fact that we represent our structure with all three different Lewis structures here. They're all obeying the octet rule, but you're having to use a little strategy here to come up with the charges. Another good example of a strategy breaking molecule, or not a breaking molecule, but one that requires some strategy, is carbon monoxide. You know, referring to my table, I would argue, well, carbon wants to make 4 bonds and oxygen 2. Clearly, if I'm going to bond 2 atoms together, that's impossible. So I might draw a carbon bonded to an oxygen to start, and then ask the question, well, if carbon wants to make 4, oxygen wants to make 3, why don't, 2 rather, sorry, 2, why don't we compromise and try it with 3? So I'll put 3 bonds between the carbon and the oxygen, i.e. have a triple bond. Now, to complete oxygen's octet requires putting a set of non-bonders there. And if I look at the oxygen at this point, it's positively charged. I have 2, 4, 6 bonding electrons. Half of 6 is 3, plus 1 set of non-bonders makes a total of, so we've got 5. This oxygen, therefore, is positive because oxygen has a 6A, is in a 6A group. Given that carbon monoxide is neutral, it must be that this carbon is negative. And in fact, I can look at this and argue several different ways. I can look at this and say, well, I have so far 3 electrons this carbon feels. If I want it to be negative, I have to give it 2 sets of non-bonders. And that's giving me a structure. The other way I can look at this is just counting valence electrons. In terms of valence electrons, carbon is contributing 4 and oxygen is contributing 6, which is 10. And notice if I started counting here, I had 2, 4, 6, 8, and that 10 is required. I need the last 2 here for the carbon to give me 10 valence electrons. But you know, another way to look at this structure again, which ends up lending us or giving us another valence, another resonance structure, is to imagine taking, for example, these 2 electrons here and moving them over to the oxygen. If I did that, I would have a structure that looks like this, where all of a sudden oxygen is obeying the usual set of rules that it likes. 2 bonds and 2 sets of non-bonders, making this oxygen, of course, neutral. On the other hand, this carbon now is missing the 2 electrons, or missing one of these electrons at least, that used to have over here. So in terms of its n, it's now 1/2 of 4, plus still the 2 non-bonders, and that equals 4. That makes the carbon neutral. So you might look at that and say, well, that's a better structure. However, notice this carbon does not obey the octet. It's an unusual structure for carbon. It has 2 bonds and 1 set of non-bonders. It obeys the charge rule, but it doesn't have an octet. It's got 2, 4, 6 electrons in its valence shell. But nevertheless, I can draw both of these as resonance structures for carbon monoxide, and they generally are. And it's interesting here because each structure has an advantage and a disadvantage. The top structure I've drawn has an advantage of obeying the octet rule. It has a disadvantage of having a charge separation in the 2 atoms. The bottom structure, on the other hand, has the advantage of not having a charge on either atom, but it has a disadvantage of having carbon without its octet. And that the true carbon monoxide molecule is a hybrid of those 2 drawings. So these represent 2 unusual structures. You don't see too many of them that obey the octet rule, or generally, but are composed of second period elements. We'll look at some more complex structures of third, fourth, and fifth period elements, and again look at this charge rule as a way to enable us to quickly come up with a Lewis structure for the more complex molecules.